Hey, before I talk into the meat of this video, I'd just like to mention that I don't need the pedal I'm building, and I'd like to pass it along to someone watching this. If you want a chance to receive it, just hit my email, listed below, with evidence of recent charitable activity like volunteering or donation, obviously sanitized of sensitive information. Once I've got a good handful of applicants, I'll randomly choose one, maybe even on stream, and if you're selected, I'll contact you to let you know, and as long as you can cover the cost of shipping, it's yours. I will exercise some discretion in terms of accepting applicants, but rest assured that no charity is too small. $5 from someone with almost nothing means more than $100 from someone who's got almost everything. I'll take this preface down once the pedal is accounted for, so if you're seeing this, you still have a chance to get in. Okay, I'm going to be cutting this a little out of order because the enclosure fabrication is actually going to be universal to all of the pack-in boards that I'll be giving out with these pedals. They're all intended to fit inside one of these 1590B enclosures like you see me cutting open right here. They're pretty small and I feel like they justify their footprint for being a single function device, and rather unsexy ones at that. In this build I'll be using two of these potentiometers. These ones I just got off the shelf at a local component supplier. You might not be so lucky, so anything that you can't find locally, I'll be supplying some links to some bill of materials pages that I've put together in the description below. I'll be doing two pots for this one that's specified on the board, and then another volume potentiometer that's actually going in front of the circuit to behave as a gain pot. So in this case I have a 1 meg pot and a 10k pot. In this phase here we're showing that we have lots of room inside the enclosure, and to kind of pre-plan where things are going to go before we start marking and machining the enclosure. Also, fun thing to note, the pots that I got from the shop are just a little too long for the nubs that I want to use. Fortunately, the metal on these pot shafts is very soft and easy to work, so just a little bit of time with a hacksaw, or if you're lucky enough to have a Dremel or a grinder, and those will zip right down, like you can see right here. So, because I didn't have the luxury of choosing a solid shaft for the 1 meg pot, I'm actually going to be mounting these sideways, because the knobs that I have are set screw knobs. And having that set screw in line with the slot cut in the pot shaft will actually help keep the shaft from deforming as you tighten down the set screw. And it also helps pre-align the knob so that the max position looks right. So here, we're just kind of laser eyeballing where we want the potentiometers to be in terms of the height on the enclosure. I'm going to try to be showing how to get these measurements with as few precision tools as possible. Like, I think I only whip out a ruler for one part of this. So, here I'm just laser eyeballing where the potentiometers want to go, and I'm just positioning one of them. Here I'm going to be using a little pad of post-it notes as a straight edge and measuring device. So here, since we marked the depth will be the same for both pots, so we can just mark it all the way across the enclosure, using the side of the enclosure as a guide to keep everything nice and square. Since we marked how far in we want one of them to be, we just have to make a mark on our little post-it note. Then transfer that mark up to the depth line. It might look like I'm a little off, but I mean, first of all, if you're just building a pedal for yourself, it doesn't have to be precision, it's yours. Confirm your measurements, make sure you're not going to be running into any conflicts. There's a saying, measure twice, cut once. Turn your post-it note around and transfer your mark to the other side. And if you do it like this, your pots should be roughly symmetrical when everything's finally drilled and sent through. So I did drill the holes for the pots off screen, but I will show you good ways to actually get your holes marked out for the other components. Here, you want to make sure you snap off these little locator tabs. Some manufacturers, I think the MXR does this, will actually use those locator tabs for their intended purpose, but they will just get in the way for us, so it's best to just snap them off. The metal's pretty cheap, so they come off real easy. With the PCB in place, and with the jacks there's still lots of room for all the other components. And so we're going to start to mark the positions for the jacks. These jacks are about 3/8, so 3/16 gives you the halfway point when you find the outsides of that. Transfer it to the sticky pad, and then you can use that mark to mirror the depth on the other side so your jacks line up nicely. If I were doing this for a production device, I would actually be making a template so that I could do a whole batch of enclosures the exact same, but if you're just making one for yourself, you don't have to fret about it that much. Here I'm actually measuring the diameter of the jack because I want the jack to be quite close to the bottom of the enclosure. So I find the diameter, cut it in half, and that will be our final depth. As you can see, I've marked those down on the side of the enclosure. And now we'll show you how I actually drill these out. So I do it in kind of 4 different operations, which sounds tedious, but it definitely is worth it. I like to use a screw to kind of act as my center punch, because first of all, they're quite sharp, so you can position them very precisely. And screws tend to be made of very hard steel, which does not wear much when you're doing these aluminum enclosures with them. You can get a lot of mileage and very precise results using a screw head. Oh, knocked the camera. I actually wasn't super happy with the position of this one, so I'm doing a second knock to get it a little more online. Again, the metal deforms easily, so you can actually get away with that. So here, just verifying the depth, checking that I'm happy with it. It's never too late until you finally drilled the hole. Next is drilling a pilot hole. Use a small drill bit choked in as far as you can to help prevent the bit from walking. And to further prevent it from walking, place your bit in your center tap and just give it one good spin. You don't want to try to go through just yet. This should show just a little bit of metal, and you'll be able to verify if you're actually in line with your center tap. And then, once you're verified, you have your little divot. You can complete the drill. Same thing on the other side. Just take a little bite. Make sure that everything's aligned as I'm happy with. And then complete the operation. I was lucky enough to find a good step bit, which as you can see has received a lot of use already, which has basically all of the measurements that I need for various holes that I end up drilling my enclosures. You can use independent bits. It all works just the same way, but it's just a little quicker and easier to use a step bit so you don't have to switch out your bits every time you need to move to a different hole size. Once you have your pilot hole, you can just kind of send it. I know, I'm making a mess. I'm sending chips and bits everywhere. I will be cleaning this up, and I do all of the other holes in a little catch box that contains all of my waste. But as you can see, they line up decently well for just doing it by laser eyeball. And still, everything fits in beautifully. Evidence that I am indeed cleaning up my workspace. I do it for you. Finally, the all-important foot switch. Aesthetically, you don't want it all the way to the bottom. Like, you want a little bit of space. So I found a good line that I think works aesthetically. The depth will actually work out just fine for where I want the, well, to make sure that the foot switch doesn't interfere with the other important components. And if you peel off just one sheet of your post-it note pad, you can get a quick and dirty center by just folding it and creasing it. The lighting kind of hides the crease, but it is pretty obvious in person. Then you can just use your laser eyeball to make sure that it's roughly centered in the enclosure, and complete your mark. Then go through the same process, center punch, pilot hole, final hole. And still, good spacing for everything. I'm also deciding to put the indicator LED just to the side of the enclosure. This one, I already have the line to keep it lined up with the foot switch, which is what I want to do. It can go anywhere you want, honestly. And just arbitrarily choose a spot that I think will look good when it's all drilled through. You can see a line from where I was originally deciding to do it topside. I decided against that. Finally, 9-volt power jack. We can actually use the same creased piece of post-it note that we used before to get our center mark. You can kind of visually index it on where the corners of the enclosure start to round off, or by visually marking it up with the screw holes that holds the bottom plate on. And then you can use the bottom of the enclosure and the side of the post-it note as your straight edge to give you a vertical line. And then you can basically arbitrarily choose a depth point. I'm going to keep mine roughly shallow, so I'll use the part itself as my depth gauge and just give a little bit extra so it's not right on the bottom. And again, comparing the part to my mark just to make sure that I'm happy with the aesthetics and the depth. Now let's get into populating the board itself and going through a bit of a circuit evaluation or a circuit explanation. First thing we're going to go through is the power supply. It consists of effectively 3 components: 1 diode, 1 resistor, and 1 electrolytic capacitor. The diode that I recommend you use is one of these 1N5817s. It's known as a Schottky diode, and in this application it has very low forward voltage drop and also serves as our reverse polarity protection. Yeah, just plunk that in there. Next is the resistor. This guy kind of helps with as I understand it, helps with ripple filtering and might behave like a fuse if something goes horribly wrong. And then finally, an electrolytic capacitor for power supply filtering. On the board I spec'd a 10 microfarad. I didn't have any 10 microfarads, so I've used a 47. Whatever fits in the hole will work, honestly. As always, bend over your leads, trim them off, and then solder to the best of your ability. I'll be skimming over this for the most part, because if you want to see it in more detail, I have another build video for one of my production pedals elsewhere on the channel. Now we get onto the input buffer. The input buffer is based around this transistor here. So for this build we're going to be omitting the input filter and this 1 meg resistor. The 1 meg pot will actually be taking its place, serving as a pull-down resistor. I did spec a bunch of these 1U caps, and I will be using film caps for this build because they look nicer and audiophiles say they perform better. But these ceramic caps here seem to be much more available in local getting spots, at least in my area. Their selection of film caps is quite distressing. So this cap here is the input coupling cap. With the input impedance performance of the transistor buffer, it should actually get you almost down to DC. You can get away with a much smaller cap. Now, throughout this build, I'm going to be using these general purpose BC547 transistors. In this particular package, the pinout is collector, base, emitter. And as long as you can read your schematic symbols, it should be pretty obvious which pin goes which. But in case the silkscreen doesn't quite convey it, the hole that is a square pad will actually correspond to the collector. Now looking at the base terminal does need to see a bias current, and that is handled by these 3 resistors here. The topmost resistor is this 33K resistor. That one's connected to the voltage supply. The middle resistor completes the voltage divider and is a 68K, which should give you a voltage slightly above 4.5 volts when it's finally applied to the base terminal. This 220K resistor, marked as M22 because I wanted to be conservative with the number of characters that I have allocated to a given component. This one actually limits the current that flows into the base of the transistor. If you end up using a different transistor than the BC547 that I have spec'd, you might want to play with this value to make sure the bias is appropriate to that transistor. Do the lead folding, snipping, and soldering dance. So this component here is actually what gives this input buffer such good input impedance performance. Most BJT-based buffers are actually limited in terms of input impedance by the voltage divider that supplies the bias current, as well as the current that actually has to flow into the base and through the emitter. This capacitor here is actually providing what's called a bootstrapping effect, which uses a little bit of positive feedback to greatly improve the input impedance of the bias network. And then finally, this 4.7K resistor is tied to the bottom of the emitter, which sets the output impedance of the emitter. In this case, it's selected almost arbitrarily. The next step is the main amplifier in our treble-shaping booster. It's based on another BC547 transistor and encapsulates all of these components here. So again, we have collector, base, and emitter, which correspond to the collector, base, and emitter terminals, as marked on the board. This is a slightly odd value component that I couldn't find at my local getting spot, so I did have to order it online. It will be part of the BOM below. It's a 180K resistor. This will actually form a part of the network that kind of derives an inline bias from the output of the previous transistor. This 82K resistor here helps form that voltage divider. Now, you could actually leave the circuit like this and it will function, albeit with significantly less gain. Because not only is the DC component of the buffer's output being attenuated on its way to the main amplifier stage, but the AC component, aka your signal, is as well. To get around that, we're actually using this capacitor here to bypass the 180K resistor. So, by providing this bypass path, you're effectively removing the top part of the voltage divider for AC signals. Again, if you find that this circuit has too much gain for you, you can omit that component entirely, but come on, we all like more gain, leave it in. So now we'll look at the emitter terminal. This amplifier configuration is referred to as a common emitter amplifier. And it produces gain that's kind of a product of the voltage divider formed by the collector resistor and the emitter resistor. So right now we're inserting the emitter resistor, which is a 4.7K resistor. You could leave the emitter terminal like this, and the amplifier will function. However, the space for this capacitor here bypasses this 4K7 resistor, 4.7K resistor. In this one, I've specified a 220 nanofarad capacitor, which sockets in right here. Again, take care on the board depending on which capacitor you use, because the marked holes on the capacitor slots are linked. Now, currently this capacitor is floating. It needs something between this B10K spot here to actually complete its reference to ground. The B10K spot is spaced such that you can drop a normal quarter watt resistor into it if you want to just have it be a fixed resistor value. But we don't want that. We're going to be using a potentiometer, so we're going to leave that unpopulated for now. Now we get to the collector terminal side of things. This 22K resistor here connects the transistor to the power supply and serves as the top of the voltage divider relationship that I mentioned before that derives the gain. It's not exactly like that, like you can look up how to derive the gain calculations for this style of amplifier, but I'm not a scientist, I'm just a guy. So, this capacitor here, much like the one that we use on the emitter terminal, is actually bypassing the collector resistor so that gain will be reduced for frequencies that are passed by this capacitor. Now this capacitor is quite small, so it's only attenuating the very highest frequencies, and depending on where you have the potentiometer on the emitter set, it might actually not be fully offsetting the gain that you're adding to higher frequencies. And of course, to complete it, you do need a jumper, because without it, that capacitor is just hanging. The space for the jumper is set that you could set a quarter watt resistor into it to, again, fine-tune that treble response if you so desire. But I don't desire, so I'm just going to jumper it. And finish connecting that collector capacitor to the power supply. Use my trusty scrubby brush to make sure that it is fully seated. Then bend your leads, trim them, solder them. Finally, we have the output buffer. This is probably the simplest part of the whole operation. We need one last BC547, same pinout, insert it the same way. It's just taking output directly from the collector of the previous transistor. This here is the output coupling cap. It's just connected to the emitter of the final transistor and is going directly to the output of the pedal. This 4.7K resistor here, again, sets the output impedance of the pedal. And finally, this 1 meg resistor here is actually serving as a pull-down resistor here to help bleed off any charge that would otherwise accumulate on the output side of the output coupling cap, and helps minimize switch popping. And with that, you have fully populated the board, and you can move on with final assembly. So, to begin final assembly, you will need a whole bunch of leads cut for this purpose. This isn't too hard to figure out yourself, you just need to know what connects to where, then you can just, as you see me doing here, compare the length you need, pull out a little bit of slack and give yourself a little bit extra to account for the ends that are going to get soldered. And if you're a smarter man than me, you would label them as you go. But I didn't do that, so I'm going to struggle a little bit. Once you have all your leads cut, you're going to want to tin them. Having a little soldering iron holder like this does help with this process quite considerably. First, you want to trim off, maybe about 1/3 of an inch or, I don't know, 1/2 centimeter or whatever that turns out to be from each lead end. I like to just kind of break the ends with these wire strippers, because then you can use the ends that are sitting there loose as an easy way of twisting all the strands as you pull off the end of the sleeving. Or insulation, I guess it should technically be called. Again, convenient little iron holder. Twist off your end, like I told you, just pinch, twist, and pull. And it braids up the end of your strand nice and neat. No fuss, no muss. Then just heat up the end, flow a little bit of solder in, and keep going down the line. You can actually get going at a pretty good clip once you get into the rhythm. I won't show all of them, just a few. Don't be afraid of those fumes. It's lead-free, so I've been told. Alright. So first thing first is actually getting the foot switch put together. You actually can buy boards that do all of this routing for you ahead of time. You just have to plunk it on the bottom of your switch and solder all the terminals. For most of my builds, I do it the hard way. I'm probably going to pivot away from that in the near future. But for the time being, this works. I'm actually going to just put up a little diagram here that shows all the different connections that you should probably make if you're doing these the hard way. if you are not a very smart person and you do it the way that I do it, I find that it's good to go kind of just one row at a time, right to left. Kind of makes it easier to keep your iron away from potentially sensitive stuff that you've already worked on, aside from this annoying little loop here. So, in the switching configuration that I'm showing you, instead of kind of hard switching the input and output like you might intuitively assume, the input is always actually normal to one of the output terminals. And the input of the circuit is actually the one that's being switched from the input of the pedal itself to ground. So, in the bypass state, the input of the circuit is seeing ground, which helps prevent the buildup of charge on any input coupling caps you might have. So, when you do finally switch the pedal, and the switch is doing its kind of mechanical changeover thing, break before make, the amount of charge that could possibly build up is probably easily offset by whatever pull-down resistor you have on the input. And then of course the output is switched between the normal input, which is sent over to the far upper right terminal, and the upper left terminal, which is receiving from the output of the effect itself. Yeah, as you can see, this little bit here is a little sketchy, so steady hands prevail. So, to complete that ground reference that it was mentioned, you do need a little tiny jumper here, going from terminal 6 to terminal 9. Just make a little horseshoe, feed it through the lugs, pull it through and snug it up. This lead here will be going to the input of the circuit. This terminal here that's doing double duty, sending it up to the potential output terminal, is the input to the pedal itself. Again, make sure you have a good mechanical connection before you get to soldering your jacks. This terminal here will actually be where the terminals on the foot switch are able to reference ground. This bottom row here functions to either ground the input of the effect circuit, or provide a ground path for the LED indicator light. If you don't use an LED indicator, you could actually just use a double pole, double throw foot switch, but those are almost as hard to find as these triple pole, double throw foot switches. Such is the nature of our lot as pedal builders. It's actually kind of funny, through my normal getting spot for most of my components, I can't actually source the foot switches that I use. I have to go to another vendor for those, because the ones that are available on Mauser, which is where I'll be doing most of the BOM, the only foot switches I can find are like 15 bucks a unit. Now, I don't know about you, but that's pretty steep for a single component that goes into a pedal. And finally, this little lead here will go to the cathode of the indicator LED. And with that, we can set the foot switch aside for a little while, as we do the other off-board connections. First things first, we've got the pots. I'm starting with the volume pot. I don't realize it in the past, but I'm actually setting myself up for a little error right now. But we'll get to that later. Man, I can't help but want to blow the fumes out of my face watching this in playback. So again, hook your lead, crimp it to the terminal, and finalize the connection. I do kind of regret that my local getting spot only actually carried a 1 meg B taper or linear taper. For a circuit with this much gain, I'd have been much happier. Yet you can see I realized that I made my mistake. But yeah, for a circuit with this much gain, I would have been much happier with an A taper or logarithmic taper, because that would give me more resolution at lower volume levels. Whereas this, it's basically just loud and louder at for like 80% of the travel of the pot. Or I guess closer to 90%. So when you're wiring up a volume pot, if you look at the pot from the back with the lugs on the bottom, you can kind of label them as 1, 2, and 3, where your signal goes into lug 1, your signal comes out of lug 2 at a lower volume level, and lug 3 goes to your ground reference. So as you can see, I'm inserting lug 3 to where that 1 meg resistor would have touched ground. Hopefully if you look at the board itself, on the backside, you'll see quite clearly that that hole is actually connected to a plane of copper on the backside, where most of the other through holes have a little bit of gap to the surrounding copper pore. And then lug 2 is going to the input, and lug 1 is going to be kept open from the input coming from the foot switch. Honestly, this soldering block is so useful. I'll provide a link to it below, as well as the BOM. I hope they still make it. So just checking that the leads have enough slack to allow for free positioning of the board. They do. These leads here will be making the power in and power ground connections. But we'll finalize those at the very end of the build. Then finally, the B10K potentiometer. We actually won't be using it as a full potentiometer. So, because of how the circuit works, because you're bypassing a resistance, and a lower resistance means more gain, you actually want it so that when you turn the knob clockwise, assuming you want more volume, more gain, you want the resistance to be decreasing. So in this case, that means you want to use terminals 1 and 2, and you can just leave terminal 3 unconnected. And yeah, it doesn't actually matter which lead goes to which side, because the resistance that we're varying is not polarized in any sort of way. If this were set up as a conventional potentiometer voltage divider, it would matter which lead goes into which hole, but since we're effectively using this as what's called a rheostat, it doesn't matter. Just make it fit. With spit and courage if you need to. Man, I've been so well behaved up to this point. What was wrong with me? And now we're finally making the foot switch to input volume connection. Next, we take the output from the circuit and connect that to the output terminal on the foot switch. And we connect the input ground to the input of the effect. Now I'm kind of trying a few different things with how I'm running my ground schemes. I know it's probably not ideal, but I'm going to be using the enclosure itself to provide the output ground reference for the pedal, and only having one point being the input jack that references the chassis to the ground of the rest of the circuit. Ideally, I would be doing it on the power jack, but because we've kind of standardized on using center negative power, thanks boss, if you get a jack that naturally sends the sleeve to the chassis, then suddenly the chassis is at 9 volts hot. And if you have everything else, grounded to your jack sleeves, then, well, you're sending 9 volts hot to ground, which that's called a short circuit. That's bad. So, I'll figure out the optimal thing eventually. Before we move on much further, let's set up the indicator LED. I've got a nice spot in the hot holder for this. The LED mounting hardware that I'm using uses this little stuffer piece, which holds everything in place. Now, it does melt under heat pretty easily, and you might end up using a different LED holder than I'm using. I'll kind of leave that up to you to source. So, I'm trying to make sure that there's lots of space between where I'm kinking the lead and that little plastic stuffer piece. So this here is the current limiting resistor. That could go on either the anode or the cathode side, it doesn't matter. In this case, I'm putting it on the anode side. Crimping it, connecting it, struggling a little bit. I'll get it, don't worry. Gotta choose the right angle of attack. Get it? Attack, because I just tack soldered it. Don't hate me, come on. I guess it's probably worth pointing out that the anode lead is longer, and on most LEDs, the cathode side actually has a facet cut into the plastic body of the LED itself. So this lead here coming off the foot switch, which will give a path to ground when the switch is enabled. That is going to connect to the cathode. Got everything crimped in place. Trim the leads. And then spread those leads out. Get them good and far away from each other to minimize the chance of your power supply shorting out on the indicator LED. Well, I guess since there's a current limiting resistor, it wouldn't fully short out, but still, you don't want it. Now this lead here will go to the top of our anode and current limiting resistor, and this will actually be connecting to the 9 volt input. Now all that's left is to stuff everything inside of the pedal. I personally like to use the little baggie that the backplate screws for Enclosure comes in to help insulate the back of the circuit board from the bits inside the Enclosure, because, you know, you don't want those weird random short circuits happening. Now, the way that I run my leads actually kind of helps suspend the PCB off of anything that could be possibly conductive, but security through redundancy, you know? So the 9-volt power jack that I have, you kind of need to screw it in place before you connect your leads. That's one thing that I'm not super happy about when it comes to this component. I gotta find something else, but I also love how low profile they are, so pros and cons. You do need to make sure that the polarity that you're soldering to is correct, because I know that virtually all pedals use a 9-volt center negative power supply. The solder terminal on the back, which connects to the center pin, in this case the shorter terminal, is the ground connection, and the longer terminal, which connects to the sleeve, is the 9-volt positive connection. For your personal build, you can do whatever you want, but if you want to have some degree of universality with power supply, it's best that you follow the same convention.